Hello friends, this is part 3 of BSc paper solution wave optics of 2022 Dibrugarh University of second semester, BSc second semester physics honors. So I have already made two parts, links are given in the description box. So before we start, please subscribe the channel, stay connected and share with your friends and hit the thumbs up button. Also hit the bell icon so that you get notified when new video will be uploaded. So now let's start. Let's start with question number 3. We have already solved 1 and 2 in first two parts. So here you see this is the third question number 3a. Derive an expression for velocity of transverse vibration along a stressed string. So here we have considered a string, stress string. So PQ is stressed by a tension T, right? Let the string be plugged at the center O. Here is the center O. This string is plugged at this point, and so string starts vibrating transversely, and this vibration are simple harmonic in nature. So now let us consider this PQ portion. Let me go to another figure here. So in this PQ portion, I have taken a very small element of length here, and the tensions on A is in this direction, and that on B in this direction. So these tensions can be resolved into two components. This is T cos theta half. So this is the angle theta and divided into two halves, right? So and this will be T sine half, right? So we're gonna get 2T sine half for these two tensions. So this is the resultant tension. So along this point CO, so along this direction. So now here you see S theta is very small. So sine theta will be almost equal to theta by 2. Sine theta by 2 will be equal to almost equal to theta by 2. So the resultant tensor become this. So now you see, let me go to the next slide. So sorry, I have forgot to add that expression for velocity. Just wait. So if you have noted up to this point, equation number 1, so here is the expression that we have got for velocity. So here for equilibrium position, the resultant tension provides the necessary centripetal force. This is given by this one. So mv square by r. Here m is the mass per unit length. So del x is the length of this element. Here we have considered this small AB element. That is the length. If the m is the mass per unit length, then the mass of this element will be m del x, right? So that is the concept here. So m del x v square by r, that gives the centripetal force, which is equal to the resultant tension, right? And from this expression we have got this expression for velocity, right? So hope you have understood this. Now let me go to the numerical part. So in the same question we have another part here. A wire gives out fundamental nodes of 256 cycles per second when it under a tension of 10 kg weight. Under what tension the string will emit frequency of 512 cycles per second. So let me show you how to solve that. So here you can see that let me write here. Okay, so let me solve. So when the number of n1, let me write here n1, 256 cycles per second when the tension is 10 kg weight, right? And if that's frequency suppose 512 cycles per second, then what will be the tension, corresponding tension? So we need to find it. So we know that n2 by n1, that's going to be equal to t2 by t1. So if you put the values here, 512 by 256 is equal to root over t2 by t1 is 10 here. So now after cancellation, if you cancel this by this, so you're gonna get 2 here, and squaring both sides, we're gonna get 4 t2 by 10, right? And from that we can write t2 will is equal to 10 for the 40. So here 40 kg, right? That is the required tension. So hope you have understood this. Now let's move on to the next question. Discuss the Newton's formula for velocity of sound and Laplace correction to the Newton's formula. So what are the effects of density and pressure on velocity of the sound? So here is the Newton's formula. So I'm not gonna discuss everything, each and every term, right? So this is the Newton's formula, and Newton's got the velocity of sound. This is the result obtained by Newton's, but it is experimentally not acceptable. That should be this one, 33200 centimeter per second, right? So Laplace made correction here. So this is the Laplace correction. So and after Laplace correction, he got this expression, final expression. This is the expression, right? I hope you will you can understand the simplifications done here. So the velocity of sound in air is after the correction, Laplace got this result, which is agreed by the experimental result, right? And this is the expression for given by the Laplace for velocity, right? So now you see, now let me tell you what correction that Laplace made to Newton's formula. So here you see, here in case of Newton's assumed that there is no change in temperature remains constant, right? During the propagation of sound, Newton considered that, but here you see, according to Laplace, so there is a condensation. Particles come near to each other and heat up, so there will be a change in temperature, and because of that, so this expression changed, right? So that's all about the correction. And here you see, this is the effect of pressure, and this is the effect of density of the medium. So what is the effect of pressure? The velocity of sound in air or gas is independent of change in pressure, and provided the temperature remains constant, right? And the effect of density, the velocity of sound in air or gas inversely proportional to the square root of density of the medium, right? So this is the relation. So now let me go to the next part. So here is the next question. It is what is the Newton's ring, that I have already written here, so read it, and let me go to the numerical part. So here you see, before going to that, let me derive the radius of nth dark ring in the Newton's ring experiment. So let me show you. Here you see, so we have considered this AB is the incident ray, and it's bent after refraction, and we have got two parallel rays, ray 1 and ray 2, right? So one is reflected from this point, incident point, and another ray is reflected after reflection of this incident ray from this point, this plain glass plate, right? One is reflected from this curved glass pieces. So, and right, due to this air film here. So now let me write here the optical path difference between the ray 1 and 2. Okay. So we have considered that incident ray AB strikes the concave piece of glass at B and reflected, which is ray 1. One portion is reflected, and the remaining portion is refracted through this air gap, and then reflected by this plane surface, and this reflected ray is ray 2, right? So we considered that. So now you see, so optical path difference is given by, del is equal to 2 mu, refractive index T cos r plus theta plus minus lambda by 2, right? So lambda is the wavelength of this light, so and T is this thickness of this air film, right? This is T. So here I have shown, I think, width, just width, right? So let me adjust. So this is the T, right? So and mu is the refractive index of air film, this air film, refractive index of this air film. Okay, so let me write the meaning of those terms I have considered here. Now you see, here you can see, if this radius of curvature r is very large, then in that case this theta, let me go to the next slide. So just wait. Here you can see, if r is very large, then and if the incident ray is normal, right, and the incident ray is normal, that means this AB, so AB is normal at this point, then this angle of refraction R, so that's going to be almost equal to that's going to be equal to 0, and theta is for very large r, so theta is also going to be negligible, so 0. So in that case this expression can be written as this. We know that cos 0 is 1, so then we're going to get this path difference is equal to 2 mu t plus minus lambda by 2. So that's going to be the path difference. This is equation number 1, suppose. Now let us take that Rn is the distance of nth interference pattern from the point of contact, right? So here you see, so this is the distance Rn, right? This is the distance Rn. Here we get, suppose, nth diffraction pattern from this point of contact where this concave shaped glass plate touched the flat one. So now you see, if you consider this triangle CMN, right, from this triangle what we're going to get, here you see, so we can apply the Pythagoras theorem that so this is the triangle CMN, and here is the right angle, and this is radius R. So as you can see, this thickness is T, so that's why this portion Cm, that will be given by R minus T, right? And this is the Rn. So applying Pythagoras theorem, we will get R square by R minus T. So let me write here, see, R minus T whole square and plus Rn square. So if you simplify this, what you're gonna get, one more thing, and T is very small. T is very small, so T square is further small. So neglected. So in that case, we will get Rn square 2 RT minus T square, right? If you expand this, then you're gonna get T square. So in this expression, and that T square will be neglected here, and this T square will be neglected, right? So neglecting that, what are you gonna get? So first, so if you simplify this, then you will get here that r square will be cancelled, right? So rn square, you can check after simplification what you will get by yourself. So this is the result after simplification, and if you expand this, then from here you will get r square. This r square will be cancelled with this r square, right? And so on. This t square is neglected, and neglecting that, we're gonna get rn square is equal to 2rt. That's what we're gonna get, right? Neglecting t square. And from here 2 small t will be equal to, here we will get rn square divided by capital R. This is suppose equation number 2. So let me write equation number 2. So now you see, for nth, what is the condition for nth dark ring? So that is the, let me write the condition here. So condition for nth dark ring, that is given by 2n plus minus 1 into pi by 2, where n is equal to 0, 1, 2, 3, and so on, right? So now you see, what you can write, if you compare this with this equation number 1, so then you will get twice n plus minus 1 lambda by 2, that's going to be equal to this 2 mu t plus minus lambda by 2, 2 mu t plus minus lambda by 2. So using 1, right? Using equation number 1. Now again we have got the expression for t here. This 2t is equal to this one, right? So here this 2t can be replaced by, we're gonna get this relation, and plus minus 1 lambda by 2. Then using this relation, using equation number 2, we will get here rn by rn square by capital R mu plus minus lambda by 2. So using equation number 2, right? So then if you simplify this, then what are you gonna get, right? So 2n lambda by 2 plus minus lambda by 2 and rn square by capital R mu plus minus lambda by 2. So this plus minus lambda by 2 cancels, right? So what we're gonna get, we're gonna get rn square, that's gonna be equal to n lambda r by small r, and taking square root on both sides, we're gonna get this result. So this is mu, right? This is not r, this is mu actually. So I made a mistake here. This is mu, right? So let me write it properly. So this is the expression for this is the expression for the radius of nth dark circle. This is mu, right? This is the expression for nth dark circle, radius of nth dark ring, right? So here we have a problem, a numerical problem. So here is this is the question, right? The diameter of the 10th dark ring due to the wavelength is given and is 0.5 centimeter. So diameter is given. Find the radius of the curvature of the length. That means length, and that means capital R should be calculated here. So we need to find the radius of curvature. So for that, so here you see, let me convert this one into meter. So 0.5 into 10 to the power minus 2 meter, and so here is the expression that 600 into 10 to the power minus 10, that's gonna be in meter. And if you simplify it, then what are you gonna get? 6 into 10 to the power minus 7, right? Meter. So we know that diameter dn of entire dark circle is given by 4 and r lambda. That's what we're gonna get. right? So now you put the values here. You will put 0.5 into 10 to the power minus 2, and root over 4. N is 10 here, and r is unknown to us. Lambda is 6 into 10 to the power minus 7 here. So squaring both sides and simplify for r, then what you will get 0.25 only squaring this, and 10 to the power minus 4, right? 10 to the power minus 4 uh, divided by 4 into 10 into 6 into 10 to the power minus 7. That's what we're gonna get. And if you calculate this result, then what you will get after calculations, so you will get the radius of curvature 1.046 approximately. So this is the radius of curvature. So now let's move on to next question. So here describe the working of Michelson interferometer. So here working principle is written. So and describe briefly how wavelength can be determined with Michelson interferometer. So here you see, here I have given the answer that how does it work. This is taken from a book. Just I have clicked the photo and pasted it here. So tomorrow, as you have tomorrow exam, so I'm not going to make this long enough. So here you can see. So, and these are the positions of maximum and minimum. Here you can see. So read it and try to understand by yourself. So here you see, and this is the way we can determine the wavelength of monochromatic light with the help of Michelson interferometer. So this is the expression for the wavelength. So here you see this one. So this is the changing position of mirror M1. So here you can see. So let me go to the diagram here. This M1, right? This is the mirror M1. So it is moved to a position. So from x1 to x2. Then the displacement will be given by L is equal to x2 minus x1, right? So and then in that case, right? In that case, this path difference will occur that light has to travel, and that will be twice L, right? Because this is the initial position of the mirror, this is the final position x1 x2. So what will be the difference in the path if this is the L, right? So same distance to be covered twice, so twice L. So that is the L here. So hope you have understood. And so if you know these two positions, then you can obtain the wavelength of that monochromatic light, right? Using this expression. So hope you have understood this. So now you see, let me go to the next question. Here you see discuss plane transmission getting. So this is the discussion of plane transmission getting. So I'm not going to explain here line by line. So I have given the answers for your exam, because tomorrow you have the exam, BSc second sem. Just pause the video and note it down. Now let me go to the next part of this question, that resolving power. I will explain this part. Okay, resolving power of the transmission grating. So here you see. So now you see. So this is a beam of white light incident on it, and suppose we have considered here this is a ray of light making an angle theta m, right? So now slightly different, in wavelength, that is lambda plus d lambda. Here its wavelength is lambda. The first one is lambda, right? So this angle is suppose theta m plus d theta m, right? So here you see, so this is the mth order maximum of So here we have considered mth order maxima of lambda, right? And this point here we will get, mth order maxima of lambda plus d lambda, and which is the position of first minimum of the order of mth order of maxima. Here we will get first minimum, just do it, first minima, right, of mth order maxima of lambda, right? So hope you have understood this. So now resolving power R, that's going to be equal to lambda by d lambda, that is suppose equation number 1, and condition for nth order maxima, is a plus b sine theta and lambda, right? And lambda. So here A is equal to width of the slit, and B is the width of separation of the width of the separation, right? So now you see for the mth order, so what will be the expression for mth order? Just replace the n by m, a plus b sine, here angle is theta m lambda. This one will be the expression, right? And for mth order maxima of lambda, and similarly mth order maxima of this pi plus lambda plus del lambda respectively will be given by a plus b sine, here that angle will be theta m plus d theta m is equal to m into, here wavelength is lambda plus d lambda, right? So this is suppose equation number 2. So now condition for minima, let me go to the next slide. So that's going to be equal to n. So here number of number of lines on the grating, capital N is the number of lines on the grating, a plus b sine theta m is equal to m lambda. Just I made a mistake here. So it should be this one, n lambda. For now you see, for the first minima of mth order, that will be given by n a plus b sine theta m plus d theta m is equal to m capital N plus 1 lambda. This is equation number 3. Let me tell you how. Suppose this is the maxima of zeroth order, m is equal to 0, So suppose we have you know capital N number of lines here, then we're gonna get this first minima at m capital N plus 1. So that's why this n is replaced by this, right? So hope you have understood this. So now just let me cut it. So here n is the number of lines on the grating. So this is what we have got. Now this equation number 2, let us multiply both sides of this equation number 2 by capital N. Let us multiply equation number 2 by capital N. Equation number 2 into capital N, and what you will get if you multiply here n, here also n, then this expression will be something like this: n a plus b sine theta m plus d theta m. On the other side, m capital N lambda plus d lambda. This is suppose equation number 4. Now comparing these two equations from 3 and 4, just wait, you can replace this left hand side by this result, because here left hand side of both equations are same. So then what you can write, m capital N plus 1 lambda is equal to m n lambda plus d lambda. That's what we're gonna get, right? Using equation number 3. So now if you simplify this m capital N lambda plus lambda, right, on the other side m capital N lambda plus m capital N d lambda, then here these two cancels out and we will get m capital N is equal to lambda by d lambda, right, and lambda by d lambda. So lambda by d lambda is nothing but the resolving power, right? So this is the resolving power. Which is equal to m capital N. So this is the required expression. So hope you have understood this. Now let's move on to the next question. So here we need to describe the Fresnel's explanation of rectilinear propagation of light and discuss the Fresnel's diffraction at straight edge. So here is the answer: rectilinear propagation. Just pause the video and note it or read it. So this is the diffraction of straight edge, diffraction at straight edge. So I'm not gonna explain these things. I don't want to make this video very long. So just pause the video and note and try to understand by yourself, because you have not enough time for preparation, because tomorrow is the exam, right? So here you see last question number 4. We need to write short notes of any two. So this is this figure. So let me tell you about this. Let me give you the answer. Here you see. So this is this figure. When particle is influenced simultaneously by two simple harmonic motions at right angles to each other, then the resultant motion of a particle creates a curve. It may be circle, it may be elliptical, it may be straight line, don't know. So it depends on the phase, right? So these curves are called Lissajous figures. Shape of the curve depends on the time period, phase difference, and the amplitude of the two constituent vibrations. So these figures are known as Lissajous figures. So this is all about Lissajous figures, and this help to determining the ratio of the time period of two vibrations and to compare the frequencies of the tuning forks. So hope you have understood this. Now let's move on to the next topic. So Stokes theorem, and here you see this states that Stokes theorem in optics. It states that when a a light wave gets reflected from a denser medium, then its phase changed by pi, right? Its phase changed by pi. So this is the statement, right? So for short notes statements not gonna be enough. So let me copy this and let me go to another slide. So let me go to another slide. So this is the statement of the Stokes theorem. So here you see what does it say, that and also mention this this is the phase is changed by pi, and the path will change by lambda by 2, right? So now you see. So suppose we have here rare medium with refraction coefficient R1 and transmission coefficient T1, and here is the denser medium with refraction coefficient R2 and transmission coefficient T2. So R1 and R2. This is transmission coefficient, right? So now, so this is the incident light ray. So here is the normal, suppose this is the normal, and incident at O, suppose this is the incident ray. Let me consider that way. One part will get reflected, another will be refracted through this denser medium, right? So this way and this way, right? So hope you know these things. And amplitude of this ray is supposed small a, right? So amplitude. So now, and that of the reflected ray will be R1 into A, and amplitude of this one will be T1 A, right? Now let us put a mirror here. So this is suppose M1 and another mirror here, M2, right? So now you see this light will be reflected back, and then again its one part will be reflected in this direction with amplitude. Let me use another color so that this light, let me write the dotted line. So the black colored, that will be in the amplitude of this R1 and A, right? Because rare to rare, it is going from rare to rare, so that's why. And one part will be refracted through the denser medium with amplitude R1A is the amplitude of this light, and after reflection it will be this, right? So hope you have understood this. Now similarly, as you put the mirror here M2, so this will be also reflected from M2. Then from this portion, one part will be reflected from this portion, right? Like this way, with amplitude here T1A, and its refraction coefficient is R2. So here we have to multiply R2. So hope these things are clear to you. Now here you see amplitude of this incident ray, that will be equal to the sum of the the rays, sum of the amplitude of those rays which are reflected from these two mirrors. So we can write A is equal to T1 A T2 plus R1 square. Let me make a correction here. Here you see this actually this one should be R1A into again R1, that should be R1 square A. So here this equation will be R1 square A. So then this A cancels. Then from here what we're gonna get? So here we will get if you simplify this T1 T2, then this A also cancelled, right? That's gonna be equal to 1 minus R1 square. This is suppose equation 1. So this is we have got from the ray OA. So here is the AO ray. This is AO ray. Right. Incident ray AO. Now let us take the ray. Let me take this one, this ray. This is suppose OB. Let me take this one, ray OB. Let me take this one. From this ray we can write 0 is equal to R1A T1 plus T1A R1. That's what we're gonna get, right? So here you see the diagram that in this direction rays are coming only, right, from this direction, and after reflection. So that's why. So here we have to write 0. Then that's going to be equal to this expression. Then if you simplify this, then what are you going to get, right? Now you see this is supposed to be R2 actually, right? So here if you take T1A common, then within bracket you will get R1 plus R2, right? So R1 plus R2 will be equal to R1 plus R2. That's going to be equal to 0, and which implies R1 minus R2, right? So here you see this relation. So here you see from this relation, refraction coefficient 1 and 2 in this two medium is here you see these two are equal in magnitude, but here this minus sign indicates that it is changed by 180. So here negative sign in this relation indicates the phase difference of 180 degree or pi, right? Which is according to Stokes law. That's Stokes theorem is proved, right? Now you see here the amount of light reflected and amount of light transmitted is same if there is no absorption. So we can write that R1 square plus T1 square is equal to 1 in that case, right? Then you see this implies that T1 square is equal to 1 minus R1 square, right? This is suppose equation number 2. Now comparing 1 and 2, what are you gonna get? So we can write from 1 and 2, replace this by T1 square, then T1 T2 is equal to T1 square, and cancelling T1 from both sides, then you will get T1 is equal to T2, right? T1 is equal to T2. So which means the amount of transmitted light in both medium is same. So hope you have understood this. So this paper is completed. Now this last topic, holography, that I haven't got this topic in the book that I am using, so that's why just search it by yourself. So thank you for watching and stay connected. If you are new to my channel, please subscribe the channel. If you think these videos are helpful, then please share with your friends and hit the thumbs up button, and also press the bell icon so that you get notified when new video will be uploaded.